Recognize that the numbers in Calc 1 are, not all of them are numbers. Some of them really are vectors because they have a magnitude and a direction. And so the positive and negative numbers that we see in the derivative are not just numbers, they're vectors. They're telling us which way we're going. Are we increasing or decreasing? Are we heading up or are we going down? In the mapping diagram, because I have the arrows heading up and down, some people draw the mapping diagrams left, right, which, I don't think about increasing this. I think about numbers going up and down. So I like to draw them vertically so that I can get a sense of numbers going up and down, but increasing and decreasing. So the arrow is pointing down here means that we're decreasing at that spot. And as we move the x up here, you see that the arrow in the mapping diagram is getting smaller, which means that the magnitude of this derivative, the magnitude of this velocity vector, if you like, is getting smaller. And when we get to 0, it's 0. Representing horizontal line, if you like. And then it gets larger as we move up. And the focus is moving along with it as well. So this is a different way to think about the derivative in this mapping diagram, but it captures some of the ideas that are in the basic definition of the derivative. Okay, let's move on. One of the big things in the, of all the rules in calculus, I want to just say one or two words about the rules of calculus. The rules of calculus, you got the product rule, you got the sum rule, you got the scale and multiple rule. You have all those rules. They can all be visualized nicely with the mapping diagram. But the one rule that you can't visualize in the graph, that you can visualize very easily in mapping diagrams, is the chain rule. Now the chain rule has to do with composition. So you really, to understand the chain rule, all you have to do is understand the composition of linear functions. Because the derivative is the best approximating linear functions. So we're going to take one approximation and compose it with another approximation. That's what the chain rule is about. So here I have a function g of x. I put it in as minus 2x plus 1. You can put anything you like in there. And the derivative of that is minus 2, so we can see that, the focus point, and we see the magnification factor here pretty easily in these arrows. Okay? It's minus 2. And I've changed my point of view. Now I'm focusing on the mapping diagram, and on the side on the other side I have the graph. So I've changed my main focus to the mapping diagram. Because visualizing the composition is a lot easier with the mapping diagram. It's really hard. We have to do all kinds of proportions to do a composition with a graph. But here's what happens when I show you the second function here. Now the second function here is 3x minus 1. So first I take the number, multiply it by 2, add 1, that's the blue arrow. I take the answer from that, I multiply that by 3, and subtract 1. And that's what the green arrows are doing. So I took one mapping diagram and pasted it into the other mapping diagram, and I follow the arrows. I start at 4, I go down, and I follow it more. Here's one you can actually follow right here. It's 0. It's 0. I add 1. And I take 1, and I multiply 1 by 3 and subtract 1. That gives me the 2 here. That's the value of f at 2. So this is the composition. This is f of g of x at 2. There's 2 for the value 0 put in. And if you move the 0, you see how the other values change. Now, it's really hard to understand what's going on in the graph, so I'm not going to spend any time on that. What is the result, then, of the composition of these two linear functions? Well, the result is, what we're interested in is, what's the magnification factor of the resulting linear function? And that's pretty easy. You multiply the factor of the first one by the factor of the second one. You have minus 2 times 3. You've got a magnification factor of -6. And I'm not sure I can show you that, but if I start at 0, we go up to 1. Let's start at -1. See that? Start at -1, it's up there. You go to 0, it's come down by a factor of 6. It's a little hard to see that, but you can trust. Maybe I can move this down. I'm not sure. Oh, good, I can. It's 6 in there.
Well, just go to -1/2 or something for your input. That should show up, right?
Well, here's 0, it's -1.
Just scale.
Let me just move this up a little bit more. All right, so here we are, minus 1. All right, minus 1 is up there. Yeah, I can see that too well. But you can see that it's making a major change as it comes down to 0. And minus 1. And these values here. That's the composition. All right, well, that's a little hard to see on this thing, but let's move to the next one. That's composition, and that's the basic reason why the chain will multiply one derivative by the second derivative. The derivatives are the numbers that are the magnification factors. Okay, so a lot of times we want to do increasing and decreasing analysis, and so we do that on the graph. We say, oh, decreasing, then increasing, then decreasing, then increasing. Well, I want to see that on the mapping diagram, and of course, where it's 0, those are our critical points. So here's the derivative. I got that graph. That's pretty easy. That's the graph. I'm not going to show you that on the mapping diagram because the visualization of the derivative is really about how the arrows change. So I'm going to hide that derivative for a second. Notice that there are zeros here, here, and here. And here's the zeros. And I put those on the mapping diagram as well. And now when you move on the mapping diagram, you can see the arrows. So as I'm moving towards, from negatives up till that first 0, you see that the arrows are all pointing down, so it's decreasing, but decreasing more slowly. And when it hits that 0, the arrow is 0, and then it's increasing, the arrow is pointing up until it hits that, not very fast, but until it hits the next 0, when next place where it's 0 again, and then it's decreasing, the arrows are pointing down until the next 0, and then it's increasing after the after. Now, those points are important points, those are critical points. They're on the x-axis. They're not on this graph, because this graph, those points have second coordinates. They're just the x's. So a lot of times when people analyze the first derivative, they draw a number line with just the x's on it. That's this number line. And you find the zeros on this number line, and that's where the function is going to be. Then you mark whether the derivative is positive or negative, and we're doing that here by noticing whether the arrow is pointing up or down when we pass through that interval. So we're actually looking at things, again, with the mapping diagram to see the signs of those derivatives and seeing how they work based on what's on the x-axis. And we can do the second thing with we can do the same kind of analysis with the concavity. We hide the increasing, decreasing. Here's the concavity being shown here. There's two places where the second derivative is 0. And what's going to happen at those spots is that up until that, the arrows are getting smaller, are bigger and bigger, and they continue to get bigger, and this is where it turns around and the arrows start to get smaller in magnitude, start decreasing, and then they go back up at that spot, and now they're going to start going back up and get steeper. So again, there's an interpretation based on the mapping diagrams for what's going on with the concavity, and that has to do with the motion interpretation of the second derivative, which is acceleration. So you can see the velocity is getting larger or getting smaller. That's the acceleration and deceleration. You can see that on the mapping diagram. The arrow is getting larger and smaller and changing the direction. Okay. Now, the differential is something that's treated kind of lightly in most calculus courses. It's also called the linear approximation. And I want to show you how the linear approximation works here. So here's our point, and here's our tangent line. Here's our value one distance away, so we see the derivative is 3 here. This is x squared at oh. Right, 2. Let me just see what's going to happen. Okay. This is the actual value of it. The value of the function at 2 is 4, right? The value of the square is 4. So that's this point here. And here's our tangent line. And here's our focus point. And there's our change for 1 unit. So if we use the derivative to estimate what's happening, we're going to see estimate being rate of 2, go up 1, up 2 from the 1, we're going to get 3 for our value. That's our change in y, change in x from our derivative. There's our focus point. And we go on the tangent line, we go over 1 and go up and see where the tangent line, our linear approximating line, are in the graph. Okay, so if we change the dx, we're changing the amount of time we're working at the derivative. So when I change the dx, I'm not going to change the focus point. I'm just going to move closer. So this point has got us added a little bit more than half, a little less than a half. There's added a half. So the change in x is a half, and our estimate for the value of the function is going to be a half times 2 is 1, added to the 1 gives us 2 as our estimate. That's the linear estimator, or the differential. If we make the change in x smaller, make the dx smaller, we get better estimates. And you can see that they're getting better estimates because the arrow to the exact value and the arrow from the estimator are getting very close in the picture over here. On the graph of the line and the graph of the curve are very close as well. We take the dx down even smaller, and we get, say, at 1/10. And we see that the differential is 2/10, and it's very hard to tell the difference between the value of the function and the value at the value at 1.1 is 1.21, and we're estimating it at 1.2. So we're only off by 100. We can also do that from the negative side as well. So now I want to tell you a little bit more about Euler's method. Euler's method basically takes the differential and uses it repeatedly to estimate the value of the function far away from where you start. So you want to make a lot of change in the x's. You do it a little step at a time. Each little step you find the dx, you find the derivative, you use that dx to make a dy estimate, and then you do it again and again. And you get a table like this. So here's our x's, here's our value of the function, here's our derivative, and here's the change, the derivative times the dx. You take that and add it to where you were before, and you make your next estimate, and you keep doing that. Here's a derivative that depends on x and y, 2x minus y. Euler's method, here's where we see the data showing up here in the mapping diagram. So I start here at 0, I start here at 0, the value is 2. That was my initial value, and I'm following this differential equation. So the first change has to go down 5/10, so here's the change of 5/10 in the first step. You keep going down, and you make a little change back up. Over here is a graph that sort of visualizes those data from this table, over here in the graph. And you can change the A and the B, but the important thing is to change the number of steps. And if you take more steps, the step size gets smaller. That's B minus A divided by the number of steps. That's the step size. And so when you make a lot of steps, you get a very accurate estimate as to how much the change is going to be from time 0. Here's 100 steps. From time 0 to time 1, you're going to have a value. If you start at 2, you're going to end up at a value about 1.46. And here's the graphical representation of that. Now that actually fits into a slope field. Let's take it back down to a number that's more tolerable. And here's the slope field that's fitted in. That comes from that differential equation. All right, so here's the crunch for the calculus course, and I want to give at least 3 to 5 minutes to the.
You've got 3 minutes. There's a class.
It's still 10 up. It's a clock here. I see it. I don't have to argue about it. The definition of the definite integral can be given by taking these sums. You can think about these as the derivative times the change in x. So it's rate of times, that's the change in position. And looking what happens as n gets large. That's just the changes. Accumulate all those changes, see what happens when n gets large, and that gets close to one particular number. That's the definite integral. That's a Riemann sum with a left-hand endpoint, if you like. Okay? So the fundamental theorem of calculus says that if that function that you're integrating is in fact a derivative, and it's a continuous function, then if you take the place where you start and you add the net change, because that's what this integral is representing, the net change, you get where you finish. In other words, the definite integral is the net change in the antiderivative f for that function p. And that's the fundamental theorem. Now I can visualize that. Now the visualization of that can be done. Somebody had it. I'm getting a sound in my head here. Let's take that down to a smaller number of n. So here's n is 10. All right, so 10 steps. This is 2x plus 1. That's the derivative. That's the rate. So I take that derivative, I multiply it by, I'm going from 0 to 2, multiply it by 2/10. Multiply by 2/10 and add it. Take that derivative, multiply it by 2/10 and add it. So that's what's happening. These are the additions. Those are represented by these points on this mapping diagram. Each small change here is a small change in y. We started at 0 here. Started at 0. So the net change here is an approximation for the actual definite integral. When I make n larger, I get a better estimate for the integral. And over here, those changes are being represented by areas of rectangles. So the net change here can be thought of as the area under the curve. It's not the motivation for the integral, it's a consequence of the interpretation of the sum ends as being small bases times heights, heights being the derivative, the p that we're using as the derivative of f. So that's a different way to get at a justification of the fundamental theorem of calculus. I want to say just a word about complex. I've got about 2 minutes on the chart here. Just a word or two about complex functions and mapping diagrams of complex functions. So, very simple complex function is a linear function that takes a complex number, multiplies it by another complex number, and adds a complex number. Very simple linear complex function. Now, the complex numbers are thought of as things that are a plus bi. When you think about the a plus bi's, the a is the first coordinate and the b is the second coordinate, so you can think about them as points in the plane. So here's a complex number. And I'm actually taking it, and here's a b. Let's make the b as 0. Let's make the b, flip a be 1. Let's take a and a b. Now what the, I'm sorry. Let's take a here and the b be 1. So multiply by the number 1. So then, as I move to z, the red point is the. And you can see that that's just a matter of adding a to it. Right? Make a this thing, so it's just like vector addition. You just add the vector a to it, we see that. Over here is a mapping diagram. So in this mapping diagram, what I have is the base plane here. That's our original complex plane. And the green plane on the top, that's our target. It's not a line, it's a target plane now. And so I draw an arrow from the point C here in the plane, point C here in the plane, to the point that corresponds to the function of z up here in the target. So that gives me a mapping diagram for this thing. What does it look like if I put in all the points on this circle? Here's what it looks like. It's just a shift of the circle, so it looks like a cylinder. All right? And if I change the radius of the circle, it still looks like a cylinder. Okay? So that's what addition looks like. What does multiplication look like? That's the interesting thing. So let's take the a and put that down to 0. Don't add anything, just multiply something. So let's multiply by 2. So multiply by 2, that's just going to spread, make the vectors go out further on the circle. And again, we can change the circle. You can see that sort of radiating. So those are pieces of a cone. There's a cylinder at well, they're all magnified, so it's all a cone. Parts of a cone. So there is that focus point from the cone. But if I make the b over here, then it turns out that multiplication by a constant, where the constant is a complex number, that involves not only the magnification, it also involves some kind of rotation. You can see that rotation quite clearly in the mapping diagram here, that as I move b, I increase the rotation. And if I get b back to a negative number, we get the thing twisting to the fact, so that the surface that those lines are forming twists so that it becomes a cone. And all those, the surfaces that are formed by those lines before it gets a cone, that's a hyperboloid of one sheet. It's a ruled surface, it's a hyperboloid of one sheet. So there's a lot of geometry in these mapping diagrams. I'm going to stop here, but I hope you've enjoyed it. Thanks for listening.
Thank you, Mike. Well, there is a class on the way in, but we know